YouTube channel. In this video, we will be discussing about how cascading failure works and how we could design resilient systems that prevent from causing global outages or blackouts. Let us start. Let's start by understanding what exactly cascading failures are. So, a cascading failure is a failure that grows over time due to a positive feedback loop. Now, what does this statement mean? What is a positive feedback loop? Say there is a small failure in a system and say a service, and that failure creates extra overload or pressure across other services, and that extra pressure or overload on other services creates even more failures, which creates even more overload or pressure on other services, and this loop just goes on. That repeating cycle in itself is called as a positive feedback loop. Let's understand this with an example. Consider there are two services and both are receiving requests equally, and all of a sudden one service goes down, and before the autoscaler could even scale and spin another healthy instance, the load increases on this other server, and as the load increases, the server now has no more resource capability to handle such loads, and this fails or becomes unavailable. Now let's understand what domino effect really means. So the domino effect symbolizes a chain reaction of failures. So in a distributed system, when one system or one service fails, then it can lead to series of subsequent failures in interconnected services in the distributed system. I'll give you a couple of real world incidents that caused global outage because of cascading failures. So you understand the importance behind building resilient systems so that we could keep ourselves equipped before the global outage or blackout occurs, right? So this is the incident report of the Google Maps outage that happened in 2022, and the Google Maps platform API was down, and this caused all the dependent services like Directions API, Navigations API, Maps API, Map Tiles API, Directions SDK, all of them went down. And another famous example that I can give you is that of the AWS US East 1 outage. So what really happened here is a change in DynamoDB's internal DNS configuration system triggered some sort of a race condition, which caused DNS resolution issues for AWS services like EC2, Lambda, SQS, load balancers, and just tuning one internal dependency across such a larger disruption across the globe. Okay, now we talked about services failing, cascading failures, and whatnot, but let's understand why services really fail. What causes a service failure? One of the cases can be where, say, a server is receiving too many requests or one heavy request, and the CPU is 100% and even the memory is full and it is not able to keep up, it is maxed out. And another case could be, say, every request coming in needs a DB connection, and if too many requests come in, all DB connections get used, and new requests then wait for a connection. This wait increases latency, and then requests start getting timeout. Also, when network bandwidth gets saturated, we could see that a service can fail. Other case could be, say, the service has a queue of pending requests. If a request arrives faster than a service can process them, the queue keeps growing. At some point, old requests are already useless because they will time out anyway, but they are still sitting in the queue consuming memory or resources, right? And other case could be, say, a service may fail because its downstream dependency is slow or broken. Your service waits for another service, that service does not reply in time, then your service also starts returning 5xx errors or timeouts. A service can even fail when a bad deployment or a bug has been introduced in the application code. So, when one service goes down, the dependent service just doesn't die immediately, right? It happens gradually. So, let's see what happens when a server dies. Server firstly becomes slow, and then latency increases. So if latency increases in one of the services, all its dependent services face the delay too. Other dependent services still keep waiting for the response from the service, and this triggers timeouts. So the timeout happens, the clients or services start retrying, and these retries creates more traffic. This overloads the system and causes resource exhaustion and whatnot, and services fail, and all dependent services also fail. And this is exactly what happened even in the case of the Google Maps outage. Let me show you. Here is the graph that Google published in their incident report. Here's what we can infer from this graph. This graph shows the global error rate on backend servers of Google Maps. During the outage around 8:30, users impact begins. That is when errors started rising because tile rendering servers were timing out and retry traffic started increasing. From there, the error rate keeps fluctuating and staying high, which shows the cascading effect. Failed requests caused retries, retries added more load, and that load caused even more failures. Around 10:40, Google took some preventive measures and immediate actions, and the mitigation was applied. You can see a sharp spike, and then the errors quickly dropped close to zero. By around 11 o'clock, users' impact ended. So, how can we improve our design and make our system more robust and resilient for such cascading incidents? So, let's discuss on the strategies for improving our system to improve resilience. One of the first things we can do is by removing synchronous calls, service to service calls, meaning we might need to switch from orchestrator to a choreographer pattern, and there may be significant overhead, so we need to be careful while choosing one over the other. And also, this doesn't mean or guarantee that cascading failures will never happen, but it only delays this domino effect, giving the system a little bit of breathing room to recover instead of collapsing immediately. In an orchestrator pattern, one central service controls the flow. It calls the payment service, waits for the response, and then the orchestrator again calls the inventory service and waits again for the response, and then the orchestrator calls the shipment service and then waits for the response. The problem is, if payment service becomes slow, the orchestrator also gets stuck waiting for the response. While it is waiting, it still holds resources, right? So, as more requests come in, more orchestrator resources get occupied. Eventually, the orchestrator itself can become slow or unavailable because the resources may get exhausted. And at that point, the failure has spread from the payment service to the orchestrator service now. And because the orchestrator service controls the whole workflow, even though inventory and shipment may still be healthy, but they don't get triggered on time. That's how one slow dependency can delay the entire flow and turn into a cascading failure issue. So a better approach here can be, especially in some cases, is the choreography pattern. Instead of one service directly calling the next service and waiting, each service can publish an event. The next service listens to that event and reacts immediately. For example, an order service can publish an order created event, payment service consumes it and processes the payment. Once payment is done, it publishes payment completed event. Inventory service then reacts to that. Now, the services are now tightly glued together through blocking calls. If payment service is slow, now the services are not tightly glued together, right? If payment service is slow, the events can still sit in the queue for some time. The rest of the system does not immediately collapse just because one service is struggling, right? But this does not mean choreography magically prevents cascading failures. The failure is just now buffered. Instead of everything failing immediately, the queue starts building up. Now you might ask a question like, what if the unhealthy service stays unhealthy for too long? So in that cases, the queue can grow too much, and when the service comes back, all the pending events may be replayed all at once, creating some sort of a replay storm. So choreography reduces direct cascading failure, but this can still cause cascading failure. Only thing is we are delaying the event. Now, another important way to reduce cascading failures is capacity planning. Capacity planning basically means understanding how much load our service can safely handle before it starts degrading or failing. Like, for example, we just don't assume that, say, a permanent service can handle 10,000 requests per second. We need to actually test it, right? So, we need to run performance tests, load tests, stress tests just to find the breaking point so that we know at what traffic level the latency starts increasing, or at what point the error starts appearing, or at what point does the service completely fail. Once we know this limit, we can design accordingly and put some safer boundaries around this service, right? And also, once we know the breaking point, we can also apply controls much earlier. Another common cause of cascading failure is badly designed retries. Retries are useful, but only when we ask these two questions first. First one is the request retriable? And second one is it safe and idempotent? Because if a request fails because of a temporary network issue or a timeout or a 503 service unavailable, retriable may make sense. But if request fails because of some bad input or invalid authentication or whatnot, retrying will not help. You're just sending the same bad request again and again. And idempotent means even if you call the same operation multiple times, the final result should remain the same. For example, reading users' details is usually safe to retry, right? But creating an order, charging a card twice, booking a ticket may not be safe unless we design it properly with an idempotency key. Otherwise, one timeout can return into uh, Otherwise, one timeout can turn into multiple duplicate orders or multiple payment charges, which is not good. And this is where retries can become very, very, very dangerous. So, retries should not be blind. They should have limits, timeouts, exponential backoff, jitter, retry budgets, and idempotency protection. Now, let's move ahead and understand what exponential backoff is, what jittering is, and how to apply retry budgets. Now, once we know a request is safe to retry, the next question is how should we retry it? The worst thing we can do is retry immediately again and again at a fixed interval, because if the downstream service is already struggling, fast retries will only add more traffic on top of the existing traffic. So instead of helping the service recover, we are basically punching it repeatedly while it is already down. That's where exponential backoff helps. Exponential backoff means we increase the waiting time between each retry. For example, instead of retrying 1 second, we retry after 1 second, then 2 seconds, then 4 seconds, then 8 seconds. So every retry gives downstream more breathing room. This is important during cascading failures because the goal is not just to get a request completed, the goal is to avoid making an already unhealthy service even worse, right? So exponential backoff slows down the retry pressure and gives system time to recover. But exponential backoff alone is still not enough. Imagine like thousands of clients all fail at the same time. If all of them retry after 1 second, then again after 2 seconds, then again after 4 seconds, then that means they are all retrying at the same time, right? All together. That creates a sudden traffic spike. This is basically called as the thundering herd problem. It is like a crowd of people all rushing through the same door exactly at once. This service may have been recovering, but then suddenly thousands of retries hit it together and push it back again and again and again. That's why we add jitter. Jitter simply means adding a small random delay to each retry. So instead of every client retrying at exactly 4 seconds, one client may retry at 3.7 seconds, another can around say 4.2 seconds, another at 5. Now the retry traffic is spread out over time. This converts one big spike into smaller manageable waves, and that makes it much easier for the downstream service to recover. The last retry strategy is having a retry budget, because even with backoff and jitter, retries can still become dangerous if there are too many of them, right? So a retry budget means we put hard limit on how much extra retry traffic we allow. For example, we can say retry should not be more than 10% of successful requests. So if the system is handling 10,000 successful requests, maybe we allow only 1,000 retry attempts. Once that budget is exhausted, we stop retrying and fail fast. This protects the downstream service from being overloaded by retry storms that we discussed about. Another important protection against cascading failures is coordinated timeouts. Say timeouts are good because they stop a service from waiting forever, right? But timeouts must be designed carefully across the whole call chain. As you can see on the screen, service A has 3 second timeout, service B has a 2 second timeout, service C has a 5 second timeout, and let's say service D is slow. The problem happens when the timeout of an inner service is longer than the timeout of its caller. So, for example, service B may wait only 2 seconds for service C, but service C may wait 5 seconds for service D. That is a problem because after 2 seconds, service B has already given up. It has said timeout. From service B's point of view, the request has failed, but service C is still waiting for service D for another 3 seconds. So, service C is now wasting CPU, memory, thread, etc. on a request that nobody upstream is waiting for anymore because service B has given up already. This is how resources get wasted silently inside the system. And when thousands of requests behave like this, imagine the wasted waits, how they can pile up, and how they can create some sort of an overload. So the rule is very simple. As we go deeper into the call chain, timeout should usually get smaller and not larger. Another important strategy is per caller rate limiting. The idea is simple. One bad or noisy caller should not be allowed to consume the entire capacity of a downstream service. As you can see on the screen, that service is being called by service A, service C, and service D. Now suppose service A has a bug. Maybe it starts retrying too aggressively or sends some sudden flood request or whatever. Without per caller limits, service A can consume most of the service B's capacity. Then even a healthy service like service C and service D will start failing, right? Because even though they did not do anything wrong, then even healthy services like service C and service D will also start failing even though they did nothing wrong, because service B is almost getting resource exhausted because of service A. This is how one bad caller can spread the failure to everyone else. So instead of having only one global rate limit, we give each caller its own quota. Like for example, service A can use only 30% of service B's capacity. Service C can use say some other portion and service D can use some other portion. Now if service A becomes noisy or breaks or fails or starts retrying or whatever, service B can reject or slow down service A's extra traffic while still keeping enough capacity for healthy callers. This is called blast radius containment. We are stopping service A from failing. We are just stopping service A from taking everyone else down. And this limit don't have to be based only on request count. They can be based on real resource usage like CPU, time, database load, memory pressure, or expensive API calls, etc. Another important way to prevent cascading failures is load shedding and graceful degradation. Let's start with load shedding. Load shedding means when the system is already overloaded, we intentionally reject some request instead of trying to process everything. At first, this sounds good, right? But it's actually very protective, because when a service is beyond capacity, accepting every request can make things worse. The service becomes slower, queues grow, CPU goes high, memory pressure increases, etc. So instead of letting the whole system collapse slowly, we reject excess traffic quickly. For example, if CPU is above 90% or the queue size crosses a safe limit, we may start returning 503 service unavailable for low priority requests. The idea here is that it is better to fail fast for certain requests than to fail all requests slowly. Say, for example, in an e commerce application system, checkout requests may be more important than some recommendation requests. So, during overload, we can drop or delay recommendations but still keep checkout alive. So, this brings us to a topic called as graceful degradation. Graceful degradation means the product continues to work in reduced mode when some part of the system is still failing. For example, if the recommendation service is down, we don't have to break the entire home page. We can show cached recommendations, default products, or some hard coded things, or just simple fallback experience, right? The user may not get the full personalized experience, but the product still works. So, load shedding protects the system by rejecting excess work, and graceful degradation protects the user experience by falling back to a simpler mode. Together, they reduce cascading failure because they stop overload from spreading everywhere. Instead of trying to keep every failure alive and killing the whole system, we are sacrificing less critical work to protect the core flow. Another important protection is a circuit breaker. Think of it like an electric circuit. When everything is healthy, the circuit is closed. That means service A is allowed to call service B normally. But if service B starts failing or timing out too many times, we open the circuit. Opening the circuit means we temporarily stop sending requests to service B. Instead of waiting and wasting resources, service A fails fast or returns a fallback response. This gives service B some time to recover. It also protects service A from getting dragged down with it. After some time, we move to half open state. In this state, we need a small number of test requests to service B. In those requests succeed, if those requests succeed, we close the circuit again and allow normal traffic. If they fail, we keep the circuit open for some more time. Attaching the image of the preventive measures that Google took to mitigate the cascading failure issue for your reference. And hope you liked this video and learned something out of it. If you stayed back till the end of the video, thank you so much for watching. And if you haven't subscribed yet, please do subscribe and like this video. And I see you in the next one.